This may look like some random cellar, but in fact, I'm at ESO's Paranal Observatory, just a few meters below ground. And this dungeon is home to some of the most advanced astronomical instrumentation in the world. To understand what's going on here, let's move up a few meters. This is what things look like above ground. As you can see, I'm indeed at Paranal Observatory. You may recognize the 4 iconic 8-meter telescopes that make up the Very Large Telescope. But if you look closely, you'll also see smaller telescopes. These have main mirror diameters of 1.2 meters and look a bit like Pac-Man, at least when they're observing. But why do we need all these telescopes? Wouldn't just one be enough? And why are they arranged in this unusual way?
The answer is that, together, these telescopes are much more than the sum of their parts. By making use of the wave characteristic of light and a technique called interferometry, we can combine them to form one giant virtual telescope, the Very Large Telescope Interferometer, or VLTI. This allows us to construct images much sharper than would otherwise be possible, and to see details in astronomical objects that would otherwise be lost. Remember the first ever image of a black hole that went round the world a few years ago? That was possible only thanks to interferometry, and involved combining observations from telescopes around the world, including ALMA. Check out this video if you want to know more. Interferometry allows us to construct images as sharp as we would get using a telescope with a diameter corresponding to the largest distance between any 2 individual stations in the virtual telescope. But this sharpness comes at a price. Our virtual telescope has huge spatial gaps where no information is available on the astronomical object we're trying to observe. It's a bit like trying to reconstruct a sentence based on only a few of the letters that are contained in it. And this is why the pattern in which the individual telescopes are arranged is so important. As Earth rotates, so does our view of the night sky. In images like this, with long exposure times, stars don't just appear as points, but as arcs or circular trails. And this is because they've moved in the sky with respect to the camera. In interferometry, we use this movement to our advantage. As the object moves across the sky during an observation, the angle at which its light hits the telescope changes. This mimics the telescopes moving. Since each pair of telescopes can only see details in one direction, it's important that they're not all in one straight line.
This is why the 4 large telescopes of the VLT are arranged in an arc like this, helping us uncover more details of the cosmic objects we're observing. They form a virtual telescope with a diameter of up to 130 meters, the largest separation between these 8-meter giants. With the 4 smaller telescopes, we're even more flexible. Unlike the large telescopes, which are fixed, the smaller telescopes can be moved along these tracks to up to 30 different locations. We can pick and choose the appropriate configuration for our science case. If the telescopes are closer together, this is better for seeing diffuse emission. Whereas if we want to pick up finer details, the larger the separation, the better. We can create a virtual telescope up to 200 meters with the small telescopes. Okay, so we need several telescopes arranged in a particular way to do interferometry. But what is all this stuff underground for? Simply put, this is where the magic happens, and the light from the individual telescopes is combined.
The black hole image I mentioned earlier is a radio image, or more precisely, it was captured using telescopes working in the millimeter part of the electromagnetic spectrum. The VLTI works with very different lights. It works in the infrared, where wavelengths are much shorter than in the millimeter. In the millimeter, the electric field oscillations are slow enough that they can be sampled and phase-tracked using electronics. This means they can be digitized. The light captured by the telescopes is recorded individually and only later correlated using a computer. But the light we want to combine for the case of the VLTI has wavelengths of only a few microns, so around 1,000 times shorter, meaning the oscillations are too fast to be digitized. While in the radio, we can combine waves electronically, in the infrared, the signals need to be combined with each other physically.
This is what makes optical and infrared interferometry so challenging, and these tunnels here a necessity. This is actually in the light path of astronomical objects many light years away, just before reaching the detector and being recorded for posterity. But how does the light get here?
The light from the target being observed first falls on the main mirror of each of the telescopes and is reflected onto the secondary, from where it bounces back and forth through a series of smaller mirrors. It is during that part of the journey that the light is corrected for atmospheric turbulence using an adaptive optics system. We made a couple of videos on adaptive optics, so check them out if you're interested.
The corrected light beams from each of the telescopes then enter their own delay line here. We have 4 delay lines, 1, 2, 3, 4. As the name suggests, the beams are delayed here. The light arriving from celestial objects at the individual telescopes doesn't arrive at the same time, so it can't be directly combined. It must be synchronized first. This is necessary so the light beams can be interferometrically combined. Essentially, you want the peaks and the troughs of the individual waves to be aligned. Otherwise, they cancel out and you lose the signal. And here is what I think is the really cool part. These movable carriages here position a mirror system such that the light waves are co-phased to within a fraction of a wavelength. This means that this whole thing here needs to be positioned to an accuracy on the micron scale. The whole process is so precise and delicate that the slightest disturbance can ruin the outcome. And what's really interesting is that these rails that the delay lines are on are curved just ever so slightly to account for the fact that Earth is round.
The light beams leave the delay lines with the correct optical path length and are fed into one of the VLTI instruments where they are combined. Just like water waves on a pond interfere with each other, creating high and low points on the water surface, 2 light beams that are combined interferometrically create bright and dark stripes. These are called interference fringes and are recorded by infrared detectors in the instruments.
The VLTI data are displayed on computer monitors in the VLT control room, where astronomers and telescope instrument operators work side by side, controlling the telescope and the instruments, running the observations and assuring the quality of the data. However, at this stage, we're far from seeing pretty pictures, or indeed, any kind of images. Instead, we see the fringes produced by the light from the different telescopes constructively interfering with each other. What we see here is the real-time tracking of the maximum of the fringes. While to the average person, or even the average astronomer like me, this looks like gibberish, I have someone here who can help us make sense of it all.
This is not telling us about the object, but about the quality of the data. So we are tracking the fringes the whole time, which means that the VLTI is working and we get coherent images, we will get coherent data from the object.
But is there anything we can tell about the object we're observing from this?
No, not directly. For this, we actually have to look at the reduced data. We have to process the data. And this we see here, visibility, which is the strength of the fringes, and the contrast of the fringes, which can be anything between 0 and 1. If it's 1, it's a point source. If it's 0, it's totally resolved. Here we have something around 0.5 or 0.8, so it's an object which is resolved, and we will see some structure in the star.
And when do we get to see an image?
For this, we need to process all the data, so this is just one snapshot, so we need lots of these data. They have to be observed over several days, weeks, and then they have to be processed, and to actually make the image can take hours if we are lucky. It can take weeks if there are problems that need to be solved in the data reduction.
But all this complex, time-consuming observing and processing is worth it, because in the end, we go from this to this. Thanks to, among other things, these cool tunnels here, we can combine the light coming from objects many light years away in a huge virtual telescope, much larger than anything we could build in a single telescope. and get some of the sharpest views of the universe achievable today. In fact, the VLTI is one of the very few optical infrared interferometers in the world. And with its large telescopes, laser guide stars, and advanced adaptive optics, arguably the most powerful. Using it, we've observed exoplanets in detail, resolved stellar surfaces, and even imaged a star in another galaxy. We've also observed black holes near and far, including tracking the motion of the stars around the supermassive black hole in our own Milky Way galaxy. A Nobel Prize-winning work. Part of the VLTI may be well hidden below ESO's Paranal Observatory, but it certainly doesn't need to hide what it's capable of. Stay tuned for many more discoveries.